Okay, so section 5.3 and 5.4, concavity and points of inflection, is basically saying we're going to use our second derivative test in order to help us draw our sketches or our graphs a little bit more accurately here, just because it's another layer of information that's helpful to us. Okay, so just a reminder here that we're going to have like concave up in our graph when the second derivative is positive. Okay, and then we're going to have concave down when our second derivative is negative. Okay. For changes at concavity, it's going to happen, or it has an opportunity to happen at the critical values for the second derivative. So the critical values for the second derivative are going to be at either 0 or when it doesn't exist. So when you have your second derivative equal to 0, that means that you could either have an inflection point or a max or a min. Okay. So inflection point, I'm just going to abbreviate to IP, max or min. Okay, and where the second derivative does not exist, it's either going to be a cusp, which is sometimes called a corner, or a vertical asymptote. Okay, and so like for inflection points, what they are is basically like a point where your graph changes to either like from concave up to concave down or concave down to concave up, and the graph continues like throughout that point. Okay, if the graph is not continuous at that certain point of your change between concavity, then you don't have an inflection point. Okay, so for example, like here, we're going from concave up to concave down, and right at that point there, that's IP, that's where our second derivative is equal to 0. So we have an inflection point because graph is continuous and there's a change in concavity. Okay. With this next drawing here, we're going from concave down to concave up, but right at this point right here, we have an inflection point because, again, graph is continuous and there's a change in concavity. However, second derivative does not exist at this certain point. Okay. And then for our third case here, we start at concave down and we go to concave up. However, there's a vertical asymptote, so like our second derivative is not going to exist where the vertical asymptote is, and because the graph is not continuous at that certain point where the concavity changes, that's why there's no inflection point. Okay. Okay. So as a note, critical values do not always result in a change in concavity. Okay, so what this is saying is just because you have your second derivative is equal to like 0 or it doesn't exist at a certain point, like that doesn't necessarily tell you enough information to say for sure that, okay, yes, concavity does change. You have to do your second derivative line analysis in order to determine that for sure whether concavity changes. So we've got a couple of examples here. We got concave up happening, second derivative at like this point here is equal to 0, but there's no change in concavity, so there's no inflection point. Similar story over here. We got concave down throughout, and then at this point, our second derivative doesn't exist because it's a corner or a cusp, whatever you want to call it. But again, no change in concavity, therefore no inflection point. All right. And then with our last example, we got concave up on both sides of the vertical asymptote. So right where the vertical asymptote is, that's where our second derivative does not exist. But there's no inflection point because A, the graph isn't continuous at this point, and B, there's no change in concavity. Okay, so for our second derivative test, if the slope at x is equal to some value c is equal to 0, then our if our slope at some point c, x is equal to c, is equal to 0, and our second derivative at x is equal to c is positive, then that tells us that we have a local minimum at x is equal to c. With the second part over here, if the slope at x is equal to c is equal to 0, and our second derivative at x is equal to c is less than 0, so it's negative, then that means that we have a concave down happening, so we have a local minimum, a local maximum at x is equal to c. Okay. So this is just like more information as to what our second derivative helps us to determine. Okay, so it basically just helps us to determine whether like the area that we're talking about is concave up or concave down, which will help us to determine if we have like inflection points or like cusps or corners, or just what the graph is doing around vertical asymptotes. Okay, so for our first example here, it says to determine the function, or determine where the function is concave up or down, state the x-coordinates of any inflection points. Okay, so when you see words like concave up or down, okay, that's kind of your big hint to figure out second derivative. Same with inflection point. That's another big clue that you need to figure out the second derivative. Okay, so what I'm going to do is I'm going to take this equation and switch it from radical form to power form. So y is equal to 2x to the power of 5 over 3. So remember that if it's in denominator, it goes in denominator. Okay, plus 20x squared, or 20x to the power of 2 over 3. And now we can use this to find our first derivative. So I'm going to go y prime is equal to, so 2 times 5 over 3 would give us 10 over 3 x, and then 5 divided by 3 minus 3 over 3 is going to give us 2 over 3. Plus, so 20 times 2 over 3 is going to give us 40 over 3. And then 2 over 3 minus 3 over 3 is negative 1/3. Okay, so you make sure, like, is there any simplification that can happen at this point? And the answer is no, so we just keep on going to our second derivative. So y double prime is equal to, so 10 over 3 multiplied by 2 over 3 is going to give us 20 over 9. And then 2 over 3 minus 3 over 3 is negative 1/3. Okay. 40 over 3 multiplied by negative 1 over 3 is going to give us negative 40 over 9. And then negative 1/3 minus 3 over 3 is going to give us negative 4/3. Okay. And what I'm going to do right now, just to make my life A bit easier for like my second derivative line test is I'm just going to factor it. So y double prime is equal to, so it looks like from both terms I can take out a 20 over 9 and then x to the power of negative 4/3. Okay, so what's left over is going to be x, and the reason why it's going to be just x to the power of 1 here is because essentially we're going x negative 1/3 minus negative 4/3, which is equal to 1. Okay, so minus, and then this is going to be 2, and then the x's are going to cancel out if we're dividing by x to the power of negative 4/3 with this. Okay, so now what I'm going to do is I'm just going to switch this into from power form to radical form. So y double prime is going to be equal to 20 over 9, and then because the x is raised to a negative power, I'm just going to put it in the denominator here. So that's x, the cube root of x to the power of 4. And then in the numerator, we have that x minus 2. Okay, so the reason why I'm switching from power form to radical form is just to make my life easier for determining critical values. Okay, so let's write that out. So critical values for second derivative. So y double prime is equal to 0 at, so this is, or actually I'm going to say when numerator is equal to 0. Okay, so that's why I'm mostly just going to focus on the factors that have a variable in it of the numerator. So then we're just going, actually, I should write this in a different color. So we're just going x minus 2 is equal to 0, which when we isolate for x, it's just x is equal to 2. Okay, and then the other critical value will be when our second derivative doesn't exist. So that's going to be when your denominator is equal to 0. Okay, so I'm going to focus on this cube root of x to the power of 4, because that's our factor with a variable in it, set it to equal 0. And then we can cube both sides. So we have x to the power of 4 is equal to 0, and then 4th root both sides. So that's just going to give us 0. Okay, so just remember for what we found when our numerator is equal to 0, so our second derivative is going to be equal to 0 at that point. We don't know for sure at this point if there is an inflection point, right? Just because if we look back in our notes, we can have our second derivative equal to 0 when the concavity does not change. Okay, so let's just write a note to ourselves right now, and I'm going to write it in a different color. So don't know yet if this is an inflection point. Need to do second derivative line test. or line analysis, maybe I should say. Meanwhile, where our second derivative does not exist, we know that this could either be a cusp, or sometimes called a corner, or it could be where a vertical asymptote is. So we'll just say cusp or corner, or vertical asymptote. Okay, so to determine for sure whether we have a vertical asymptote or not, we need to look at the original function to see if there's anything in the denominator, right? So because in the original function there is no denominator, that eliminates the possibility for a vertical asymptote. Okay, so it has to be a cusp or a corner. Okay, so I'm just going to write out what I just said. Look at original equation factored denominator to determine if there is a vertical asymptote. Okay, but like I said, since there is no denominator in our particular example, that means that this has to be like a cusp or a corner, whatever you want to call it. Okay, so I'm just gonna move up here. So sure, I'll just go. Actually, maybe I'll just draw just a line to help keep this information separate. Okay. So what I'm basing this line analysis off of is the second derivative. So I'm just going to write it out so that I don't have to keep on scrolling up and down. So 20 times x minus 2 over 9 cube root of x to the power of 4. Okay. So just going to make my number line here. Okay. And we said that our critical values were at 0 and 2. Okay, so at when our second derivative is at 2, our second derivative is, at x is equal to 2, our second derivative is equal to 0, and at x is equal to 0, our second derivative does not exist. So I'm just going to relay that here. Okay, so it doesn't exist here, and it's 0 here. Okay, so I'm just going to choose some point that's smaller than 0 for this first part here. So let's say -1. So 20 is still going to stay the same. So it's still going to be positive, but -1 would cause this factor to be negative over, and then for this, essentially what this would be positive, because -1 to some even power would be positive. Okay. So our numerator would be negative. Negative divided by a positive is still negative, so this is concave down. For the next one, let's just say I pick a point of 1. So 20 is still positive, and I'm going to put that for the remainder of them. And then this factor here is still going to be negative, and our denominator is still going to be positive. So again, we still have concave down. for the next section here, let's say we pick x is equal to 5. So that's going to have x minus 2 be a positive value, and then denominator will still be positive. So now we have concave up. So now we can say with certainty that we have an inflection point here because there's a change in concavity, and like our graph still exists like throughout as we go across x is equal to 2. Okay. Okay. So the question is asking us to state the x coordinates of any inflection points. Okay. So for my answer, I would say inflection point. Actually, I'm just going to say IP for inflection point at x is equal to positive 2. Okay. The question also asks us to determine where the function is concave up or concave down. So I'm going to say concave down at, so from negative infinity up to but not including 2, concave up at 2 to positive infinity. And there's our answer. Okay, so just don't be so quick to call your critical values for your second derivative inflection points. Make sure you do your second derivative line analysis, so this thing right here, to figure out for sure. Okay. So moving on to the next example, we're asked to sketch the function, and it gives us a pile of information. Okay, so this has like a lot of pieces of the puzzle kind of coming all together all at once, and like I find it super helpful just to make notes as you read through this stuff, just to help you get an accurate answer. Okay, so limit as x approaches 0 from the right, our function is going to go to positive infinity, okay, or our y values of the function are going to go to positive infinity. Okay, so what this means is that I have a vertical asymptote at x is equal to 0. So what I'm going to do is write on my equation, and maybe I can change my line here. I'm just going to draw my vertical asymptote. So I'll just go vertical asymptote at x is equal to 0. Okay, and then I'll just make a little sketch right here, just to remind myself when I'm putting everything together. So like that, and I might have to clean that up in a little bit. Okay. The next part here says the limit as x approaches positive or negative infinity. So this part right here is your dead giveaway that it's a horizontal asymptote. So this is saying we have a horizontal asymptote at y is equal to 7. Okay, so if I apply that on my graph here, so shapes, and I can go, we'll say I'll mark out that this is y is equal to 7. So horizontal asymptote at y is equal to 7. Okay, so there's that. For this next part here, this is saying that our first derivative at x is equal to negative 6 and x is equal to negative 2 is equal to 0. Okay, so essentially we're just saying that we have either maxes or mins. We don't have enough information to say whether they are for sure like either a max or a min at this point in time. Okay. This next part here says that our first derivative at x is equal to 0 does not exist. So that tells us that we have like either a cusp or a corner, whatever you want to call it, or a vertical asymptote. Okay, but also at like our function at x is equal to 3, we're told that, well, it does exist. It equals -1. So that already eliminates that we have a vertical asymptote because we're being told our graph does exist here. Okay, so I'm just going to write in, this means function exists. Therefore, corner or cusp, whatever you want to call it, at x is equal to 3. Okay, and also we're told that our second derivative at x is equal to 3 does not exist. So that's just like more proof that, okay, it's a cusp. Okay. For this other part here, so second derivative at -8 and -4 is equal to 0. Okay, so what that means here is that our slope is not changing, essentially. Okay, so those points are going to be important. And also we're told that our second derivative is positive between -8 and -4. So what I like to do is, like, I just like to, like, and you can just lightly sketch this in with your pencil. I just like to draw like concave up for where that applies, just to help me. Okay, and then it says it's concave up between 0 and +3. So I'm just gonna do that. And these can just be like little lightly drawn in. Okay, and then our second derivative is negative from -infinity to 8. So that means concave down there, and concave down between -4 and 0. And then concave down at or between 3 and +infinity. Okay. So I'm just going to mark out some points here. And yeah, sure. I'll do them with purple. Okay. So we're told, let's see here. So I'm just kind of going on at -6 here. So -6, we know we have a max or a min. Okay, we're not told the exact y value of this, and we're not told about any x-intercepts, essentially. So, like, as of right now, it's hard to say, if we have, what y value our max or min has, right? But hang on one second here. But what we can do here is that I'm gonna put it here, okay, and just say like slope is equal, or our first derivative is equal to 0. Okay, and the reason why I'm putting it kind of like lower is because we're told that this section right here is concave up. So it's going to be more helpful or easier to draw that if we put our point lower down. Okay, we're also told that at x is equal to -2, that we have a max or min. And if I look at this section here, it's concave down. So that means that there's going to be a maximum. So I'm going to put my point where slope is equal to 0 higher up, just so that it's easier to draw. Okay. All right. So kind of like taking a look at this first part here, it's concave down and we have a horizontal asymptote to pay attention to, as well as this minimum point. So how I'm going to put that all together is I'm going to go like so. Oop. One last thing I should mention is this tells us that our slope is not changing at x is equal to -8. So I'm going to try and do my best to draw a straight line at x is equal to -8. And then, yeah, make sure my end behavior does not cross that horizontal asymptote. Okay. And also we got like a non-changing slope at x is equal to -4. So at -4, I'm going to try my best to draw a straight line, but also go up to my maximum. Okay, and then we have this vertical asymptote, so the end behavior of my graph cannot cross that. So then I'm going to go down like this. Oop, I'm going to try that again. And another reason why I know that I'm going down is because I say so right here that I'm concave down. Okay, so for like our positive x values, our first part is concave up, and then our next point is concave down. And then remember that we have a cusp at x is equal to 3. Okay, and another piece of information we have is that our function at x is equal to 3 is -1. So I'm going to draw a point like roughly at -1, and I'm going to label that out. Okay, and I just got to make sure that I draw a cusp here. Okay, so I'm going to have to resketch this part here. So again, I'm doing concave up. We're trying my best to. There we go. And then concave down. But also pay attention to my horizontal asymptote. Okay, so I know that my graph kind of goes back up towards y is equal to 7 because of this horizontal asymptote, and we're told that our function approaches y is equal to 7 as our x values go towards positive infinity. So one thing to notice that's kind of weird is that our graph does cross this horizontal asymptote at y is equal to 7, which, like, based on your previous classes in like math 30-1 or 20-1, like, it's a little bit confusing because, like, you were most likely told, like, asymptotes are where your graph does not exist. However, like, this kind of section is sort of like in the middle. It's not at the ends of the graph. Okay, so asymptotes describe where the end behavior of a graph is going to approach. It doesn't have any bearing on like the middle behavior of a graph. So that's why our graph can cross the horizontal asymptote there, is because that's the middle behavior. It's not at like the end behavior. And when I say like end behavior, I'm meaning like extreme negative x values or extreme positive x values. Okay.